They're looking for me. I'm teaching your class. All right, we can start. So then when I attended your lesson, let's see. It's five things. Okay, we can begin. Today we are going to look at direct current circuits. Okay, direct current circuits. Just a moment. Let's try to. Okay, when we talk about direct current circuits, what comes into our minds is that, of course, if there is direct current here, then there should be also what is called alternating current. So there is either DC, which is direct current, it's either DC or there is AC. So this is what you call direct current, and this, of course, is called alternating current, like that. Now, when we talk about direct current circuits, we are talking about a battery source or the source of an EMF. That is the first thing that we are talking about. So first thing first, let's look at sources of EMF. I'm sure you've seen this before. EMF, this is nothing but electromagnetic force, like that. That is the meaning of EMF. Where do we get this EMF? For example, you have in a circuit, this is our positive terminal, that is our negative terminal. This, which is a cell, so battery, is the source. This is the source of EMF. So we are saying the source that maintains the current in a closed circuit is called the source of an EMF. So a battery or a cell in a circuit is what we actually refer to as a source of EMF, where EMF is nothing but electromagnetic force. All right. Okay. Here, when you talk about direct current, what should come into your mind is that we have a source, which is our cell or a battery. And here we are talking about DC. When we start talking about AC, AC is alternating current. That AC is what you receive in your homes. In your homes, you don't receive DC, but we receive AC. That is alternating current, so to say. Now, we have established that in a given circuit, for example, if you have a battery, this is our small circuit. Maybe here we have our bulb. Then we have a source here. This source is actually what is the source of EMF, which is electromagnetic force. Now, any device, of course, that increases the potential energy of charge circulating in circuits are sources of EMF. So this is just an example. When you've been asked, for example, in a test, in an exam, state one example of a source of EMF, what you say is you can either mention a cell or a battery, and you have a full mark, as simple as that. Okay, now the SI unit, for EMF is what is called the volt. That is the reason as to why on your cell, if you go to the market and you buy a small cell like that, that's your positive, this is your negative, you realize that you have somewhere where it's written 1.5 volt. This 1.5 volt is what is called the electromagnetic force, which is measured in volts. And the apparatus that you use to measure that is what is called the voltmeter. All right. So how do we define this EMF then? We know that this EMF is actually given out by a cell. How do we define EMF? EMF, in simple terms, is nothing but the work done. So EMF, this is the work done per unit charge. That is the definition of EMF, the work done per unit charge. In other words, the work that is done by moving one charge throughout the circuit is what is defined as EMF. So we are saying the work done per unit charge. In order for charge to actually be moved in a circuit, it demands that we actually require some amount of force that we need here to push the charge in a complete circuit. As long as the circuit is not complete, we realize that there will be no flow of charge, and hence we will not have current passing in that. All right. Okay. So let's look at the terminal voltage or the EMF. So in a real battery, for example, any battery like this one, there is what is called internal resistance. So any battery that we have, for example, there is some resistance inside this battery, but in most cases, it is ignored. But in reality, that resistance is actually there. Why? Because any material, despite how good it has been made, there has to be some resistance somewhere. All right. So moving forward, how do we then determine the internal resistance of a given battery? Okay. Now, of course, this is what is called the terminal voltage. In other words, we can actually measure if we connect this, of course, to a voltmeter in that way, then we can actually measure the actual voltage between these two terminals. And of course, how do we do that? So what we have, for example, in this case, if you connect the positive and the negative charges here by connecting it to a voltmeter, you are able to get this reading here. If the battery or the cell, it is still very good, your voltmeter will read 1.5. If the cell is getting damaged, then this number may drop to about 1 volt or 0.8 volts. Then you are saying your cell is damaged or your cell is finished. You need to throw away and maybe replace that cell, for example, in your clock, for example, in your remote control at home. For example, this is what happens when it's because the amount of EMF that the battery is able to produce has gone down. And that means the internal resistance has actually increased in the battery. All right. Okay. Moving forward, let's look at resistors in series. How do we connect resistors in series? Right. Okay, so we look at resistors in series. Remember yesterday we looked at capacitors. How do we connect capacitors in parallel? How do we connect capacitors in series? So today we are going to look at resistors in series. In that. So, how do we connect resistors in series? Of course, we know, for example, the symbol, we know it very well from high school. It's just like that, or whichever way you want to put it, in that way. So that is just a symbol for the resistor. So how do we connect them in series? What we have is that we have our connecting wires. We have R1 there. We have R2, then we have our source of EMF down here, have our voltage there. This is R1, this is R2. So here what we see is that, of course, this is our voltage. Then what we have is our current will be moving in this direction. In that way, remember, the positive terminal is this one. This is the negative. So electrons are moving in this direction and they are opposing the direction of current. The positive are moving in this direction and they move with the direction of the current. How then do we have the total resistance? How do we add the resistance for R1 and R2? We remember very well that for the potential, the change in the potential is equal to, of course, we have I R in that way, where I is the current and R is the resistance. So that gives the change. So this becomes straight away, that is I. Then you have R1 plus R2 in this way. Then what else? From there now you need now to push them on the other side. So that means the equivalent, when these are connected in series like this, it means that the R equivalent must be equal to R1 plus R2 plus R3 plus dot dot dot. You can be adding them like that. So that is how you connect them in series straight away. What about in parallel? How do we connect them? You can put it here. For example, we have our resistor there, and we have another one there. This is our voltage source. Then we have other one and other two in that way. Then we are now looking for the total resistance in this way. Right. That means here, first of all, let me put the diagram so that we are able to see it well. Let me put it here. So this is in parallel. That is our source. Okay, if you realize in the first diagram, we had, of course, our voltage here. This is our current I, but when it reaches here, the current here has to now get, because it reaches this junction. This is R1, this is R2. That becomes our I1, this becomes our I2, like that. So that tells us that the moment resistors are actually connected, all right. Okay. I'm seeing a comment. Of course, where did you go to? We are coming to Ohm's law. Just take your time. We'll come to that. Don't worry. Just take your time. We'll get to that. Don't be in a hurry. We'll be learning slowly but sure. I've seen your comment. All right. So what is there is that when this current I reaches this junction, what is happening is that depending on the resistance from R1 and R2, it means that this I, which is our I total, will actually split into I1 and I2 in this way. That is what is, that's what you should actually put in mind. Now, the moment it splits, what we see is that I must be equal to I1 plus I2. Then from there, we know that the change in the voltages, of course, we can measure from this and that, and then we'll be able to get the actual voltages that we have in that line. Now, how do we then get the resistance? From here, we know that 1 over R equivalent must be equal to 1 over R1 plus 1 over R2. This, of course, you can reduce it to R1, R2 into R1 plus R2. There are times you'll be asked to say, this implies that R equivalent must be equal to R1, R2 over R1 plus R2. At times you may be asked to show this in an exam. To show that for any given two resistors, show that the equivalent resistance is actually equal to R1, R2 over R1 plus R2. This is how you do it. Just put a simple diagram, try to explain the aspect of the current, then use our simple equation there, and then what you see is that this actually gives you the R equivalent, and then you reduce that and flip it at this point. When you flip this, it comes to that. Okay, let's move on. Okay, now we go to Another very important topic, which is just connecting to this, it's just part and parcel of this, which is called the Kirchhoff's law, or the Kirchhoff's rule, just like that, whichever way we want to put it. So how do we determine, or how do we define this rule in terms of our electric circuits? Right. Okay, I'm saying good morning, sir. Good morning to you. I hope you are enjoying yourself at home and having good breakfast this morning. If you don't have, like me, just continue listening to the lecture. When you start working, you'll be having breakfast. All right. So we go to what is called the Kirchhoff. Of course, let me get the correct spelling. That is okay. Now, what does this rule tell us? The first thing that we should know, remember when we had resistors in parallel, like that, we realize that the moment this I is approaching a junction here, it means that this is moving in this direction. It means that this I had to split into I1 and I2. And we agreed to say, at this junction, what it means is that I must be equal to I1 plus I2. That is very crucial. Now, let's look at an example. First of all, if we are asked to say we should state Kirchhoff's rules, what is there are actually two of them, which is very important. The first one is that the current that is actually entering the junction is equal to the current that is actually leaving the junction. So this is rule number one. So here we know that the current that is entering a junction must be equal to the current that is leaving a junction. In our diagram, for example, let's put an example here. Let's say this is our junction. Then we have so many connecting wires that are coming in there. Let's say this is I1, I2, and this is I3. Then we have that which is I4 and I5 in that way. So what this means is that we know that I1, I2, and I3 are actually entering this junction, and we see that I4 and I5 are actually leaving this particular junction. So this means here I1 plus I2 plus I3 must be equal to I4 plus I5. This is the first rule. So you have to note that this rule will help you a lot in solving these electricity related questions, and it will help you solve and reduce those huge diagrams that you may come across and simplify them into more simpler circuits, so that now you'll be able to solve them as you wish. Okay, now we have sorted out the first one, which is the rule number 1. Now we need to get to the next rule. Of course, we are saying the second rule, in this case, just take that nicely so that you'll be able to see. Okay, the second one is that the sum of the voltage gains over a loop must be equal to the sum of the voltage drop over the loop. This is the second rule, which is very simple to explain, of course. Okay, let me just clear this part so that we can put our second rule here. I'll go back to our simplest diagram that we had, which is resistors in parallel. This is how we had our diagram. Okay, so putting in mind that this is R1, this is R2, then we have our voltage, which is here, in other words, our EMF. So we know for sure that this voltage is nothing. Of course, we have our I here, which is the current. We defined the voltage to be equal to I multiplied by the resistance. But we know that this resistance is actually 1 plus 2, which is R1 plus R2. Then the current here is the same. So it means that at this particular point, we have I R1 in that way. Then again, we'll have I here and R2. So it means that here, our voltage or EMF becomes I R1 plus I R2 in that way. So what does this second law actually state? This is rule number 2. What does it state? Here, what we notice is that the voltage across here, we have, of course, V, and then there we also have another voltage. Let's call this V1 and this V2. So the moment the voltage comes in here, it will actually have some resistance due to R1. It means that the amount of voltage that is going to reach R2 will be less than the amount of voltage that actually enters R1. Because of the resistance of R1, it means that the resistance, the voltage has reduced a little bit in order for it to reach R2. What does that tell us? It means that V1 will be actually greater than V2. But the second rule tells us that V1 plus V2 must be equal to V. That is the second rule. So here we are saying the total EMF of that is different components in a circuit must be equal to the EMF at the source. In other words, this is what we are saying. So this must be equal to the EMF at the source. That implies that V must be equal to V1 plus V2. This is the second rule that you have. At times, you may be given V, and also you may be given V1. Then you are told to determine what V2 would be. But at times, the circuits may not be as simple as this. This is the simplest you can ever have. But at times, we can make this a little bit complex just to check on how much you've gotten the knowledge. Okay. Okay, let's look at an example for the day so that we can try to see how we can solve this. Okay, let me put the diagram. So you can do this even behind your book where you are writing some few notes. You can put the diagram there. So this is our example. In that way. So our diagram. We have our first resistor there. Then we have our second one that way. Then of course we have another one here that way. Then we have V1 and V2. This is our V1. Then we have our V2 here. This is V2 in this manner. Okay. So then, of course, we have R1, which is our first resistor, which is there. Then we have our we have I1 there. Then, okay, let's check something here. Okay, there's a question. This rule, is it only applies to resistor in parallel only or even in series? It applies in both. It's not just in parallel, but the one that I've given is just an example of parallel, but it applies in both parallel and series. Thank you so much for that question. All right, so that is our I1. Then we have R2. That is I2 here. That means the other one is, that is R3. Sorry for that. This is the one that is R2 and I2, I3, R3. Then the data that you've been given, the question is, what is the current through and voltage over each resistor? So the question is asking us to say, what is the current here and there and there? Also find the voltage across each of these resistors. So the moment you have such a question, first of all, what you do is you need to identify which ones are your junctions. We know that the first junction that you can identify is this one. This is your junction number 1, which you may call J1. The second one is here. We may call this junction 2, which is our J2. Now, the next thing that we need to know is now to find out what data have we been given. From the question, we see that actually R1 is equal to R2, right? Which is equal to R3, and this is equal to 3 ohms. That is the data that we've been given from the question. Then also we've been given that V1 must be equal to V2, right? Which is equal to 12 volts. So here we have 12 volts, and there we have 12 volts. That's what we've been given. Now, the first thing that we need to know is that where is the current going? Where is the current going? So we know that this is the negative terminal here. If this is negative in this way, and this is positive, this is negative, this is positive. It means that the current is actually going in this direction where there is the positive terminal. This is where we have our current. And as it is going in this way, it is this current. What is the name of this current? We are calling it I3 in that way. So we see that this one, which is actually at this junction, we realize that, in fact, in this case, if you look at the way the circuit has been designed, we realize that there's a positive here, which is coming in this direction, there's a positive here going in that direction, and also this negative, so it means that we also have the current here, which is I1. Now, depending on which you want to take as your positive and which one you want to take as your negative. So if you take the left-hand side to be positive, it means that you have to maintain that I1 and I2 will be positive. If you take the right-hand side to be positive, you have to maintain that I3 must be positive and the other I1 and I2 must be negative. Why? Because of this junction that we have here. There's a current that is actually entering the junction, and there's current that is actually leaving the junction. So how do we do that? The first step that we have, of course, we put that as our equation 1. Okay, as our equation 1, we know that I1 plus I2, this I1 plus I2 then must be equal to I3, because I3 is the one that is entering the junction, then I1 and I2 are actually leaving the junction. Remember the rule number 1, the amount of current that is entering the junction must be the same as that which is leaving the junction. How do you put that? Straight away you have I1 plus I2 minus I3, or let me just don't jump there, must be equal to I3. This implies that I1 plus I2 minus I3 must be equal to 0. That is straightforward mathematics. Okay, now the second one is now the one that looks at the loops. Remember, the second group is looking at the loops. We take this to be our first loop in this way. This is loop number 1. Then this one, of course, gives us loop number 2. So the first one is, let's look at the left loop in this way. So that is number 2. We look at the left what? The left loop. So what is a loop? A loop is a complete circuit. If you look at your circuit here, from this point, going all the way up to there, come back here and back to this point, that gives you one loop, which we are calling the left loop. Then the other one is from here, going this way, come up, you go to your left, then come down. That is the second loop that you have. Okay, now how do we solve for the first loop? We know that the total voltages across R2 and R1 must be equal to our total voltage, which is what? Which is V1 here. So straight away we know that this V1, we know that V1 must be equal to V, which is, that is V for R2 and the voltage across R1 and the voltage across R2 combined must give us V1. So straight away, this becomes the current, of course, that is I R1 plus I R2 in that way. Now, what you realize is that the current is not the same. The current that is passing through R1 and R2 are not the same. Hence, this time around, you need to indicate that this current is specifically for R1, that current is specifically for R2. Then this implies that V1 minus I1 R1 minus I2 R2 must be equal to 0. So you leave that as your equation 1 here. This becomes your equation 2. Then you move on now to the second loop. In that way, you move to your second loop. What do you have under the second loop? Okay, here we know that straight away you can start making replacements. We know that V1 from our data, which is here, is 12. So you put your 12 there, which is actually 12 volts. We know that the current here, straight away, I1 multiplied by multiplied by the resistance, which is R is the same as R1 is the same as R2 is the same as R3. So this is minus 3I1 minus 3I2 must be equal to 0. So you state that clear. Okay. Now, the second point is where you look at the right-hand side, which is this loop here, loop number 2. When you look at loop number 2, you have V2, which is this one. So it means that under V2, the voltage across R3 and R2 must be equal to, when you add these two, they should give you V2. It's that simple. So what is the meaning of that? What we see is that V2 plus I3, R3 plus I1, that is I2, R2 must be equal to 0. Why? This V2, if you check very well, this voltage is going in this direction. This voltage is going in this direction. Like I mentioned, if you take the left-hand side to be negative, then your right-hand side must be positive. If you've taken your left-hand side to be negative, remember that your right-hand side must remain as positive. On the right loop, what do we get? Okay, let me just check something here. Okay, there is a comment. Can you please have time for the lectures? I'm sure your timetable has been sent to you. Just clearly check. If it has not been sent, remind me. I hope you have my line. I can send it to you. Okay. All right. Now, like I said, the next one is our right loop, which actually gives us V2 plus I3 R2, of course, V2 plus I3 R3 plus I2 R2 must be equal to 0. In other words, when you have V2, in this case, this side now we are taking it to be negative. I mean to be positive, since we took the other side to be negative for the other part. So it means that on the third part, we know that that is the right loop. What we see is that V must, which is V2 plus I3, that is R3, must be added to I2, R2, which should be equal to 0. This, of course, is 12 plus 3I3 plus 3I2, which must be equal to 0. Since R3 is given as 3 ohms, then R2, of course, is here, which is R2 is the same. So you put 3 there. The voltage, of course, is here, which is 12. So you are able to get that from your data. That becomes your equation number 3. Okay. Now, I'll wrap this part. First of all, let me put the last one, which is outside the loop. We have dealt with loop number 1, which is this one. Loop number 2 is that one. But in most cases, students forget that actually here there are actually 3 loops. There is one, which is this one. The other one is that one. Normally students will end here. But there is a loop which is now the one which is outside here. How do you deal with it? That's what is very important. Okay. All right. Okay, there's a comment here. There is no time allocated to the lectures. Okay, just for the sake of those that have no time, the lecture time is 9 hours. We should start. So if the timetable is not showing the lecture time, it means that I think it was just an omission, but your lectures should start at 9. Yeah. Okay. Okay, I've seen that, Mwangara. Is it Mwangara Fellowship? Yeah, I've seen that comment. So the lecture time is 9 hours, and I'm sure you have the lines for your lecturers. Please get in touch with them. If you don't have the lines, please find out from your fellow students, and your class reps must be following up in case you've missed any of the lectures. Okay, so outside the loop, I want to leave this so that it can be our reference. So I will put it down here as our number 4, which is outside the loop, the outside loop. This outside loop is actually combining this V1, V2, R3, that is what I3, R3, then I1, R1 going in this way. We are skipping this part on the last loop like that. Okay, now what about the outside loop? So the first thing that we realize is that when we are going in this direction, here we realize that this is the positive, it will move in this way, then there's the negative there, which is pushing in that way, but the current is going in this direction. So that means there should be anything that opposes the motion that you are taking. Anything, if you've decided to go in this direction, then there is a current or any resistor that is opposing. It means that it becomes a negative. If you go in this direction, whatever is going on this direction, it means that you take them as negative. So the direction that you are taking is what becomes the positive. Whether you move in this way or you move in this way, you will get the same exact answer at the end of the day. But what is important is to take note which one takes the negative and which one takes the positive. So here, what we see is that V1 must be, well, that is V1 minus R1, that is R1, I1, R1 minus. So if you realize this I is going in this direction. So the direction that we have taken is this. So whatever opposes our direction becomes negative. So that's why we are saying V, which is V1 minus, because I1 is going in this direction, that becomes I1, R1. Then from there we check, where is R3 going? R3 is going in this direction, but we are going in this direction. It means that this also becomes negative. Don't forget about this. So that becomes minus I3, R3. Thereafter, we have this, of course, is going, this voltage is going in this direction, but we have decided to move in the clockwise direction. So this again becomes negative as well, because it is opposing where we are going. So that becomes minus V2, which is equal to 0. So straight away, what you see is that if we make replacements here, we realize that this becomes minus 3i. Then, of course, V1 is the same as V2. So V1 minus V2, that gives us 0, which is 12 minus 12. Then we see that this implies that minus 3 I1, right, which is R1, I1 minus 3 I3 must be equal to 0. So if you push this on the other side, what you see is that this 3 and that will cancel. Then the next thing that we see is that I1 must be equal to what? Must be equal to minus I3. Okay, that becomes our number 4. So now you have equation 1, you have equation 2, you have equation 3, and you have equation number 4. And then now you can combine the equations so that you are able to get the actual solution that you are looking for. All right. Now, the first step is to combine equation 1 and equation 4. So if we combine equation 1 and equation 4, what do we have? So the first step, you combine 1 and 4. So let's look at what 1 is giving us. 1 is saying I1 plus I2 minus I3 must be equal to 0. This is our equation 1. What is number 4 saying? Number 4 is saying I1 must be equal to minus I3. I1 must be equal to minus I3. This is equation 4. So, depending on how you want to combine it, you can actually, where there is I1 in equation 1, you can put minus I3 here. Or you can put, where there is minus I3, you put I1 and see what happens. So what we see from here is that I2 must be equal to 2 I3. So this implies that I2 must be equal to 2 I3. Okay, we take note of that as our star. Then when we combine, of course, after we have this, we know that from here what we have done is that where there is I1, we have put minus I3. So this minus I3 minus I3 becomes minus 2 I3. Then we take it on the other side, which becomes positive. That's why we are here. That's where we are. Okay. Okay, let me just check the comment. Okay, the diagram that I'm using is actually in the slide. That is an example. You check it. It's the example is given there, and the solution is actually there. I was just checking the comment. It's the one that is actually in the slide, and it has been solved there. The answer is in red. So I'm just trying to explain what that answer is, because they've done a lot of shortcuts there. But you need to know what is behind those solutions. Thank you so much for that comment. All right. Now, what we have is that after we've done this, if you go back to equation number 3, we see that equation number 3 has only I3 and I2, but I2 is the same as 2 I3. So look at, so we put in equation number 3. Let me pick equation number 3 from there. We have 12 plus 3 I3, then plus 3 I2, which is equal to 2. This is our equation 3. But now, here we know that I2 is equal to 2 I3. So we bring this to where there is I2. We bring this, all out of this, to come and replace that. And this straight away gives you 12 plus 9 I3. Because this is 3, that becomes 3, multiplied by that becomes 6. 6 plus 3 becomes 9. So straight away you have 12 plus 9, I3 must be equal to 0. In that way. So straight away from here, you make I3 the subject of the formula, and then you realize that what you get is I3 must be equal to 4/3 amps. In this way. So you've now found what I3 is. Then next, you get this I3 and plug it in here. You multiply by this, you get I2. After you get I2, you now plug I3 and I2, then you get I1. This is how you do it. And then you get that as a solution. Right. Okay, let me just check some of the comments. Okay, Okay, let me say you bear with me. The network is not too good today. So at times it cuts, then it has to reshuffle again. I think that's why you're not seeing clear. But we'll try to make sure that you get the best out of it. The network is not too stable, and this has been the challenge on this end. Okay. All right. So in the end, what you realize is that I3 is here, like I was explaining. Then you get this I3, put it here, you find I2. Now that you have I3 and I2, you put it in here in equation 1, you have I3 and I2, then you find I1. And then you realize that the solution, of course, that you are going to get at the end of the day is that I1 will be equal to minus 4 over 3a, and I2 will be equal to 8 over 3 amps. Like that. Okay. I think that is all about the example. All right. So, what is the time? Okay, I think we are going to end here for today. I don't want to continue to bombard you with a lot of stuff since some are complaining that they are not seeing too well. So I think we'll end here for today. Thank you so much. Enjoy the rest of the day. And please, if you have any question, like I've mentioned, there are some of you I'm attending to, just please get to my WhatsApp or get my email. You send some of the solutions that you are doing in your tutorials, then we can discuss them privately. So there are some that we are helping, those that are trying to do the questions. So try to do the questions on your own. When you have problems, please get in touch. We are here to help you understand what you are doing. Thank you so much. Enjoy the rest of the day.